So thank you very much, as well as for the kind invitation for today's talk. So I assume you can see my screen well. Thank you. Okay, so I will focus today on semi-transparent CMOS backplanes for advanced near-to-eye microdisplays, which will be mostly used in optical see-through augmented reality. My group has recently moved from Fraunhofer FEP, so another Fraunhofer institute, into Fraunhofer IPMS, and IPMS stands for Institute for Photonic Microsystems, and I think such sort of microdisplay is indeed a nice example of a photonic microsystem. Yeah, I mean, just to give you an idea, we are based in Dresden, Germany, or the southeast of East Germany, and specifically the ecosystem here in our area. It's very important also for the sort of works that we are doing. So let's say we are very closely related to microelectronics, and we are also collaborating with those fabs that are really in walking distance from our side. So here is the Dresden airport. We are situated here. And there are the fabs of Global Foundries, Bosch, Infineon, X-Fab, and some others really close. And that is really a kind of prerequisite for what we are doing here. With respect to microdisplay technology itself, you might more or less briefly distinguish between emissive ones, which are mostly today non-transparent, as well as some other technologies like reflective, transmissive, and scanning devices. I will focus today on the emissive ones, and there are two major emissive microdisplay technologies, OLED and silicon. And the next speaker, Jan Gülling from CubeDot, might also focus a bit more on micro LED. Later on. So, and the major difference between those emissive and all the other technologies is that the light source and the image modulator is the same, and that actually provides the best and form factor for such devices, since you don't need an external light source as a separate device. And as I already mentioned, mostly the backplane, so it's typically a CMOS chip, are non-transparent. And now the idea is to make those transparent to make for optical see-through devices even better form factor approach than we have today. So what are the common challenges for optical see-through devices? So to optimize field of view, very high resolution, PPI and PPD, brightness, color weight, form factor, eye box, focus Q, mutual occlusion, and of course manufacturing cost, and all of them simultaneously. And there are a few types of different optical see-through approaches so far. So for instance, a 45 degrees flat combiner or build bars optic, which is rather simple, but also comes with a few issues like form factor versus field of view efficiency and also optical distortion. There are also freeform approaches that are very compact, but also come with optical issues, for instance, with respect to Wirtgen's accommodation conflict. And rather popular today are waveguides, so specifically also diffractive ones. They provide a rather good trade-off in form factor, eye box, and cost. But, and that is really an important issue, specifically in wearable applications where you always have a very limited battery capacity, is their low efficiency, their low optics efficiency. So, and often a narrow emission from the light source is required. And narrow is in terms of angular emission as well as also spectral width emission. There are also a few other approaches. Okay, but these waveguides typically require very high luminance light sources due to these low optical efficiencies, and therefore mostly LCOS, liquid crystalline silicon, also MEMS-based spatial light modulators, as well as micro LED are being considered necessary as the light or image source in such waveguide devices. But the drawback is the very high power consumption that is required. For instance, Gertech has shown a monochrome micro LED based projector device for near to eye consuming 1 watt monochrome, and for RGB even 2.5 or 2.4 watts. And this is just too much power consumption for wearables. And why? Because the battery capacity in a wearable should not be more than 1 watt hour and should still enable 12 hours of continuous operation. And that actually means that the entire electronics, including not just the display, but also sensors and microprocessor, microcontroller, and so on, should consume less than 20 milliwatts. And the light engine itself only 5 milliwatts or even less. And that is not achievable with all the other devices. But the issue is, since OLED can typically not, or let's say, cannot reach the brightness level that is required for waveguides due to the rather wide emission spectrum and the too low luminous flux, OLEDs are typically excluded for such engines, display engines with waveguides. So, and there's a solution to come along with semi-transparent emissive microdisplays or microdisplay backplanes. And one effect will be that the display itself becomes a combiner. So nowadays we have such sort of setup, a non-transparent display. We have these combiner optics with exit pupil expander, and now we move over to a semi-transparent microdisplay backplane, so you can directly look through the microdisplay, and you still have some additional optics in front to provide the virtual image. So that would be the new approach. Then that means we don't have optical or significant optical losses anymore, and we can really live with a moderate light engine luminous flux in the setup. That means OLED will become sufficient again, and OLED on silicon is already a mature technology. Micro LED will still be valid and appreciated for that approach, but micro LED, at least in my opinion, maybe Jan will look at it differently, still has to become mature to some extent. So, and there are two general optical setups. We call it sparse pixel versus cluster approach. So the general idea is to really leave transparent circuit layout spaces in between either pixels or clusters. So that's a cross section of a general emissive micro display. So here in that case, we have seen typically non-transparent silicon backplane, and we have the organic or OLED front plane. And as I mentioned here in the statement, we leave some space in between individual pixels or in between groups of pixels, and this space in the backplane will be transparent or semi-transparent, and then we will also get an overall semi-transparency. And this is achieved by making use of SOI, so silicon on insulator, CMOS backplane wafers. So they actually feature a thin active SOI layer on embedded or on top of a silicon dioxide. And in so-called bulk silicon, this active layer would be in a non-transparent silicon layer itself. And now we have, as a so-called handling wafer, we have another silicon substrate underneath. So what we now do is that we perform the processing based on our design of the SOI wafers at a silicon foundry, then receive their wafers back. We continue with the emissive or OLED layer or front plane stack on top of that, and then we actually remove the silicon handling wafer, and then we have this transparent spaces in between the individual pixels or clusters, as I have shown before. So this gives you an idea. So here, this is a backplane, including several micro display devices on the SOI wafer. It's not yet transparent there. Then we perform the OLED front plane integration, and then we apply this transparency process, so the handling wafer removal, and then the devices become transparent or semi-transparent. And this is what we currently have. So such sort of device. It is how to say, designed in clusters. So we have 7x4 clusters, and each of the individual clusters has 256 by 256 pixels. It can also be used in an RGB arrangement. Then you have half the resolution, and the individual clusters are roughly 0.9 millimeter by 0.9 millimeter in size. The individual sub-pixel size in such a cluster is 3.5 micrometer. And the cluster pitch is 2.2 millimeters. So the 7x4 clusters at 2.2 millimeter pitch. And that means we actually now put here, you can get the idea of the 7x4 cluster. And now we put a micro lens array it's the same size, so 7x4 micro lenses on top of this emissive semi-transparent backplane. In our first approach, we have actually achieved 22% of optical transparency. We have shown this last year already, and this year we have been able to improve that to 45%. And that is some sort of image taken through the optics, so of course including the micro lens array and through the semi-transparent backplane. So let me conclude with some outlook. Of course, high brightness is still a topic. Although the luminance that for optical see-through that is required by the semi-transparent backplane approach can be much, much lower. So typically 5,000 nits or so will be completely sufficient. High resolution is obviously a topic. I already mentioned the 3.5 micron dot pitch in the semi-transparent device. But we have also shown the 2.5 micron dot pitch on a non-transparent backplane, but on a 300 millimeter, 28 nanometer CMOS backplane node. Embedded sensing, embedded connectivity. Of course, also micro LED might be an interesting topic also for the semi-transparent approach, but for instance, also for extended spectral emission and detection ranges, and obviously new form factors. So transparent, I already discussed, for instance, also for use in future smart contact lens applications, but also such sort of curved devices that can really enable again increased or improved form factor of such optical devices. And that's it. And still, let's say the obvious AP questions. So what can IPMS do for you? So of course we can perform such customer-specific micro display design and also pilot manufacturing. We are working with silicon foundries on both 200 and 300 millimeters and make the OLED front plane in-house. And of course we can provide such sort of backplane transparency process. And we are looking for partners, for instance, for collaboration with wafer level micro optics designers and suppliers, as well as with system integrators. And that's it. Thank you for paying attention to my presentation.